On the night of July 4th, 2026, as millions of Americans looked to the skies to celebrate the nation's 250th Independence Day with one of the largest fireworks displays in its history, another aircraft was descending through those same skies. That same night, Delta Flight 1076, an Airbus A319 carrying 52 passengers, 2 pilots, and 4 flight attendants, was on final approach into Chicago Midway, descending from Atlanta with its gear down and flaps fully extended. At just 200 feet above the ground, an explosion jolted the aircraft. The pilots believed they'd been hit by a firework. One radioed air traffic control, "We're just hoping it was just a mortar that went off underneath us, but we definitely felt a big bang." The controller replied that other aircraft nearby had reported the same thing. The plane kept descending exactly as commanded, engines steady, controls responsive, cabin pressurized, and touched down safely seconds later. All 58 people on board walked away without a scratch. It looked like luck. It wasn't. The outcome of that landing had been decided decades earlier, in the specifications of the airplane itself. Quick one before we get into it. If you're enjoying this, do us a favor and drop a like, and hit subscribe if you haven't already. Let's continue. The Airbus A319 is a narrow-body, twin-engine airliner, the shortest member of the A320 family, at 33.84 meters long, with a 34.1-meter wingspan, wider than the aircraft is long, and standing 11.76 meters tall. It carries 132 passengers in 3 classes, 12 Delta First Class, 24 Delta Comfort, and 96 Delta Main seats on board. All seats feature in-flight entertainment systems, USB ports, and power outlets. The aircraft is also Wi-Fi equipped. It is powered by 2 engines, either the CFM56-5 or the IAE V2500, each producing 100 to 120 kilonewtons of thrust. Airbus built it by shortening the A320's fuselage by 3.73 meters and removing 7 fuselage frames, while keeping the same wings, engines, cockpit, and flight controls as its larger sibling. That's why an A319 pilot can climb into an A320 or A321 cockpit and fly it without any extra training. The two share a single type rating. It first flew on August 25, 1995, was certified after 350 hours of flight testing across 2 aircraft, and entered service in April 1996 with Swissair. Since then, more than 1,480 have been delivered, and across the whole A320 family, an aircraft takes off or lands somewhere in the world every 1.5 seconds, adding up to over 117 million flight cycles. That volume is the real proof. A design flaw doesn't survive 117 million cycles unnoticed. The fuselage skin is built from high-strength aluminum alloy, with newer aircraft using aluminum-lithium alloy in sections, lighter and more corrosion-resistant, without losing strength. The wing skin uses the same family of alloys but varies in thickness along the span, thinner near the tip, thicker at the root, where the bending force is greatest. That thickness isn't padded for safety margin, it's set by the loads the structure actually carries, because every extra kilogram burns fuel over a 30-year service life. The skin is asked to be only as thick as it needs to be, and the structure beneath it is built to pick up the rest. The skin itself isn't one continuous sheet either. It's overlapping panels riveted and bonded onto the frame, so a hit to one panel stays contained to that panel instead of spreading. That exterior is built to take hail, bird strikes, runway debris, and lightning. An airliner is struck by lightning on average once or twice a year of service, and it's designed to shrug that off and keep flying. Behind that skin is a semi-monocoque structure, circular frames spaced every few inches down the fuselage, tied together by longitudinal stringers, reinforced longerons, and structural beams. Airbus could have built a fuselage where the skin alone carries the load, lighter and cheaper, but rejected it, because a skin-only structure has no backup path if it's damaged. Built into that frame are tear straps and crack stoppers, reinforced strips placed at intervals whose only job is to stop a crack at the edge of one panel before it can travel into the next. A lesson the industry learned from early jet-age fuselage failures, now standard on every modern airliner. The wings work the same way internally. Spars run root to tip carrying the bending loads, while ribs along the span hold the wing's shape under aerodynamic pressure. Where the wings pass through the fuselage, The wing box is rated to several times the load of normal flight, including the full weight of the aircraft pressing up against the wings during a hard landing. The Airbus material choice follows the same logic. Composites in the tail fin and rear fuselage, because carbon fiber resists fatigue, cracking better than metal over decades of service, and titanium and high-strength steel at the engine attachments and landing gear, where the stress is repeated and highest, and weight takes a backseat to strength. All of this sits under two combined design principles: fail-safe and damage-tolerant. Fail-safe means the structure has multiple load paths, so one part failing doesn't bring down the whole. Damage-tolerant means engineers assume some crack, dent, or impact is inevitable at some point across a 30-year service life, and design the structure to keep carrying full loads safely, even with that damage present, until it's found and repaired. Airbus could have designed to a simpler standard instead. Build each part to survive its expected lifespan and replace it on schedule, but that offers no protection against damage nobody's scheduled for. It's also why any aircraft is pulled from service after an unusual impact, no matter how minor it looks. Not because anyone assumes the worst, but because the design demands verification before assumption. The A319 is fly-by-wire, part of the same A320 family that brought full digital fly-by-wire to commercial aviation, replacing mechanical cables and pulleys with electronic signals between the pilot's controls and the flight surfaces. That was a deliberate trade. Fly-by-wire weighs less than mechanical linkage, responds more precisely, and lets computers enforce limits the pilot can't accidentally exceed. It's also why pilots fly with a side stick instead of a yoke, freeing up the instrument panel across the whole family. The system itself runs on primary flight computers, backed by secondary flight computers, backed by further redundant channels, a direct answer to one question: what happens if a computer fails mid-flight? Nothing important. Another channel takes over instantly. The windshield is built from multiple laminated layers of glass and polycarbonate, certified to withstand a bird strike at cruise speed, because a layered structure holds together even if the outer layer is damaged. The wing leading edge is reinforced beyond the rest of the wing surface, since it's the first point of contact for hail, debris, and birds, the highest probability impact zone on the whole aircraft. The engine nacelles have their own independent containment structure, so an internal engine failure stays inside the housing instead of spreading to the wing or fuselage. The landing gear is built to absorb the equivalent of a controlled crash on every single landing, oversized deliberately, because unlike flight control computers, gear has no redundant backup if it fails. Each of these is over-engineered against the specific threat it's statistically most likely to face. A series of individual trade-offs, not one blanket rule applied everywhere. Before certification, the airframe is cycled through fatigue testing equivalent to tens of thousands of flights, watched closely for the first sign of a crack, and tested to multiples of its intended service life, so the certified limit always keeps margin in reserve. Windshields go through bird strike testing, an actual carcass fired from a cannon at operational speed straight at the aircraft's most exposed surfaces. Flight control systems go through redundancy testing, with individual components forced offline one at a time to confirm the aircraft stays controllable in a degraded state. The certification standard, broadly, comes down to this: survive an unexpected impact at the altitude and speed you're most likely to face it. It was never built around one specific threat. It didn't need to be. Now let's return to that approach into Midway. The bang the crew heard was the fuselage skin, absorbing a localized impact exactly the way its layered panels were built to. The plane didn't shudder, because the frame beneath that skin distributed the force before it could concentrate into something dangerous. The crew didn't hesitate, because the fly-by-wire system showed no loss of control authority. And the aircraft was pulled for inspection at the gate not because anyone thought it was broken, but because damage-tolerant design calls for verification every time, not assumption. What the passengers heard was a bang, followed by a controller calmly confirming other firework reports nearby. What an engineer sees watching the same 60 seconds is a structure, a system, and a certification process, each doing exactly the job it was built for 3 decades before that firework was ever lit. An Airbus A319 got hit by a firework 200 feet above Chicago on the night America turned 250, and it landed like nothing happened. It didn't survive because of luck. It survived because it was built to. If you got something out of this, hit like, send it to someone, subscribe if you're new here, and stick around, because what almost happened on the next flight I'm covering makes this one look routine. See you in the next one.